Alright everyone, welcome back. I'm going to pick up where I left off in the last carbohydrates video. I'm much smarter about this time. This time my cat is not in the room with me, so he can't bully me as I'm trying to explain this stuff to you. So hopefully this should go a little bit more smoothly. Alright, so this is where we left off. So we were talking about the structures of the different monosaccharides, right? And we can have, varying lengths depending on how many carbons that we have present. We can have aldoses, we can have ketoses, excuse me. One unique thing that we see once we get to the 5 and 6 carbon monosaccharides is that we see cyclization. Right? These linear structures, these linear sugars, they can actually react with themselves to form rings, to form cyclic compounds. All right, let me give you an example here. So I'm going to put D-glucose up here. And if you remember D-glucose, that's an aldohexose. It's got 6 carbons, including an aldehyde group. So I'm going to draw it out real quick. Okay. So what can happen in 5 and 6 carbon monosaccharides is, if you take a look here, that next to last carbon, in fact, it's the highest carbon number that has stereogenic properties, right? This is carbon number 5 in this case, and it's the last stereogenic carbon. All right, the OH group that's on it, right? Oxygen, all these oxygens have unshared pairs of electrons, right? That makes it slightly nucleophilic. It's a weak nucleophile. We've learned previously in organic chemistry that carbonyl carbons are really good places for nucleophilic attack, right? Including in aldehydes and ketones. So what happens is this OH will loop around and attack that carbon. And you're going to form a bond between that oxygen and that carbon. And at the same time, a pair of electrons, pi electrons, is going to move up solely to oxygen. And when you do that, you form a cyclic structure. Wow, that is an ugly, ugly ring. Well, I'll try to fix that. You know, I'm not very artistic in general, but especially drawing... Whoa, okay. Especially drawing on a tablet, for some reason, I'm even sloppier than I usually am. It's not much better, but it'll do. Okay, so basically you create this ring now. All right, and let me finish out the structure, and then I'll kind of explain where various stuff is. Okay, so that oxygen right here that's located on this carbon has now looped up and attacked that carbonyl carbon. All right, so if we're looking, this oxygen right there is that one right there. All right, this carbon, this carbonyl carbon, is the one that's located here. And you can tell pretty easily because it's got the O minus on it. And then you have the other groups that are placed. All right. You'll notice that the ring here uses straight up and down, This is called a Hayworth projection formula. We've done these before in organic chemistry. Um, and the H's and the OH's do have particular directions that they need to go. They align with the way they were in the D-glucose form, right? So if you had an OH on the right in the linear structure, it's going to be pointed down in the cyclical structure. If it was on the left in the linear structure, it's going to be pointed up in the cyclic structure. Okay? All right. Then you have a negative O and you have a positive O. That can be fixed really easily by having this oxygen grab a proton from the positive one. All right, so when all is said and done, when I erase this, I'm going to draw the final cyclic product. I did a really bad job with that ring as well, but you can see. That's what we end up with. All right. Couple of things about this. First, I want to highlight the equilibrium arrows. You don't just completely convert all of the linear form into the cyclic form. You reach an equilibrium where they're actually constantly interconverting from one form to the other. Okay? So, even though the cyclization does occur, you're never going to completely get rid of that linear form. There's always going to be some there. All right? The other thing I want to highlight, and I'm going to erase part of this, is that in this case we're forming something called a cyclic hemiacetal. All right. What, you may ask, is a hemiacetal? Well, if you had me in organic chemistry, we talked about it. So, Amber, I know you've had it. I don't know about Sarah and Rachel, but I'll review it again for you so you can see it. Here's the general structure of a hemiacetal, right? It looks something like this. You have a carbon. It's got an R group, so basically a carbon chain attached to it. It's got an H. It's got an OH. And it has an OR group. Okay? So, cyclic hemiacetal just basically means you have this arrangement but in cyclic form. So, if you look right over here at that little fella right there, that carbon, you'll see it's got an H, it's got an OH, one half of the ring is led off basically by a carbon chain on the bottom, and then the other half is led off by an OR group. So, this is a cyclic hemiacetal. By the way, this particular carbon has a special name. This is referred to as the anomeric carbon. All right. So the anomeric carbon is just the carbon that used to be the carbonyl carbon. Now, in cyclic form, it's referred to as the anomeric carbon. All right. One thing you'll notice about the anomeric carbon is, yes, because originally this group was an aldehyde group, right? So we didn't have particular groups on the left or right because we just didn't have bonds on the left or right? So, but we do now because we have 4 bonds. This carbon does have a distinct OH and an H attached. We said with all the other ones, if the OH was on the right, in linear form, it went to the bottom. If it was on the left in linear form, it went to the top. With the anomeric carbon, it could go either way, right? Why can it go either way? Well, remember, everything goes back to organic chemistry, right? When you have a nucleophilic attack on a carbonyl carbon, what's the hybridization of a carbonyl carbon? It's sp2. What's the geometry? It's trigonal planar. Where can it be attacked? From either side equally. So, in a nutshell, what that means is, at your anomeric carbon, you could end up with this arrangement where the H is on top and the OH is on bottom. Or you could have it vice versa. Where it was like this. And you do get both. You have multiple forms. If the anomeric OH is pointed up, we refer to that as beta. We would say we have a beta arrangement of groups on the anomeric carbon. If the anomeric OH is down, it would be alpha. That's going to be important to remember, because when we start putting these rings together, putting these cyclic monosaccharides together, we're going to form things called alpha linkages and beta linkages, and it's all based on what direction your anomeric carbon is pointing. Okay? So, when we cyclize glucose, we form a hemiacetal, specifically a cyclic hemiacetal, and we form an anomeric carbon. Depending on which way that OH ends up pointing will determine whether it's alpha or beta. All right, let me show you another example. This time I'm going to use, instead of glucose, I'm going to use D-fructose. And the reason I'm using this is because this one is going to be a ketose. It's similar, but it's slightly different. Okay, so it looks very similar to glucose. The big difference is that instead of having an aldehyde group at carbon number 1, you have a ketone group at carbon number 2. Okay? It's still, the carbonyl carbon is still the spot for nucleophilic attack, and you still use the same group, right? You always use the OH that is on the highest number stereogenic carbon. And attack basically works the same way. You're going to attack that carbon, move a pair of electrons up. All right, pay close attention to the number of atoms in your ring now. All right, we have this oxygen right over here. We have this carbon. That's 1, 2. And then the other things that are linked within the ring are this, this, and this. That's 5. So this is actually going to create a 5-membered ring, so a pentagon, with a connection between your oxygen and your ketone carbon. Okay? All right. So this basically works the same way, right? We have attack of that carbonyl carbon by the OH, and then you're going to have a proton transfer between the two oxygens, right? And this is what we end up with. 1 second. Let me look at something real quick. I'm wondering if I drew this correctly. Give me just a second. Oh, I did not draw it correctly. I knew I didn't get something right there. All right. 1 second. That should be an OH. Okay. Okay. So, this is going to be your anomeric carbon. This oxygen, obviously, is going to be right here. This carbon is the one that got attacked right over here. Okay? And so, that carbon also has the CH2OH as well as the OH. Just like we saw before, we can have alpha and beta at the anomeric carbon. It just depends on which one is represented. I went ahead and represented the alpha one here. But both will form. These are still going to be in equilibrium with each other. Since the carbonyl group was in the middle of the ring as a ketone group, that's why it doesn't make as big of a ring as the other one did. All right. Instinctively, I always want to say any questions because that's like a thing I do in class. But since you're not here, I guess you can't I can't ask any questions. I could say, do you have any questions? And you could pause and think for a minute. So, yeah, let's try that. All right, anyway, but yeah, so with cyclization of something like fructose, a ketose happens in the same manner that it does with an aldose. Except, it doesn't make a hemiacetal, it makes a hemiketal. Subtle difference. Very, very similar to a hemiacetal, right? You have a carbon. It's got an R group. It's got an OH. It's got an OR group. But instead of having an H, it's got another R group on it. Right? So if we look at our anomeric carbon right over here, it's got an OH, check. It's got an OR group, check. It's got this CH2OH, that's another R group, and then it's got this half of the molecule. So that's actually a hemiketal. Ketoses cyclize into hemiketals. Aldoses cyclize into hemiacetals. That's how it works. All right. So that is the discussion of monosaccharides. I covered most of this this is all stuff I covered within the talk there. Just a couple of things here. Some terminology. When you get those 5-membered rings, the one like I just drew for fructose, just generally speaking, if they're 5-membered, they're called furanose. And if they're 6-membered, like the glucose one I drew, that is called a pyranose. Not a chemical classification at all. It just has to do... It's kind of stupid, actually. But if you look at it here in this next slide, you see the structure of a molecule called furan. They're called furanoses just because they kind of resemble that structure. That's it. That's all. Right? So, again, Kind of dumb, but it is a bit of terminology that's referred to, and so you got to be familiar with it. All right, so there goes all the stuff I just talked. I think I'll keep going. She can send me a text if it's something important. All right, so let's talk about reactions of monosaccharides. What can you do with them? Well, there's a number of things that you can do with them. One of the most important things that they can do is they can be involved in redox reactions. It's very, very easy to oxidize and reduce certain types of sugars, right? You see all those OH groups. Really, really good points for oxidation reduction. There's a really fun demonstration that I like to do. Sadly, I can't do it for you guys because, well, this is a video. But if I had you in the lab, I'd show you. It's called the exploding. Exploding is not a good term. It's more of a flaming gummy bear. You can set a gummy bear on fire by putting it into a molten solution of molten sample of potassium chlorate, and then the sugars within the gummy bear will actually be oxidized by the oxygen that comes out of the potassium chlorate. Specifically, only certain types of sugars can undergo a reaction like this. These are called reducing sugars. All right? And in essence, you have to have an available free carbonyl group to be called the reducing sugar. So glucose, for example, right? Glucose in its linear form is an aldehyde. It loses that aldehyde form once you cyclize, but remember, there's an equilibrium there. You always have some of that free aldehyde group present, right? So glucose is a reducing sugar. Fructose, same thing, right? Fructose is a ketose. You have that ketone group. You cyclize, but you always have some that is present there through the equilibrium. So you can have that. You can have a redox reaction at that ketone carbon. You're going to see others later on that are not reducing sugars. We do have sugars that do not have aldehyde or ketone groups available. So if you tried to toss them into the gummy bear reaction, they wouldn't do anything. Gummy bears, though, guess what they got? They got a lot of glucose in them. Some of them have fructose in them, and maybe other simple sugars as well. But I know they got a lot of glucose, which is a reducing sugar, and you see a really, really dramatic redox reaction. So I encourage you to get on YouTube and just look up Flaming Gummy Bear and watch a demo of it. It's pretty neat. That's a dramatic one. You know, they are involved in other redox reactions that are much more tame than that one, and those are going to be the ones that are important biochemically. Sorry, voice is getting a little raspy. Excuse me. All right. Basically, the whole basis for the redox is that, and we learned this in organic chemistry as well. We said, this goes all the way back to reactions of alcohols, and there's lots of alcohols present in sugars as well. We said that alcohols can be oxidized and form carboxylic acids, right? Well, carbonyl compounds, they can too. So whenever we have a reducing sugar, right, whatever group you have that's getting oxidized, whether it's that aldehyde or ketone, or even an OH, that's going to be turned into a carboxylic acid. All right. Otherwise, you can also produce actually, I was sitting here debating whether I really want to get into this or not because I'm getting a little off topic. I don't want to stray off too much. It's really not that important, but let me just highlight the fact that other redox products. Let's just say that carbon dioxide is another type of redox product that's commonly formed. You can also form something called lactones, which is a cyclic ester. Right? Basically, what this is, it shows you that there are a variety of products that can be made through redox of reducing sugars, and we do see these various types occur in the body, depending on what type of metabolic reaction is being catalyzed by what type of enzyme. Again, a little off topic here, but it's just kind of a cool photo. Look in your PowerPoint on a real computer to see it. There's something called the Tollens test. This is actually frequently done in organic chemistry labs. I haven't done it in a while. I don't know about you guys last year. But you can actually take a free aldehyde group, such as in glucose, and you can react it with a silver-based compound. Sorry, I'm trying to catch up on my computer. Yeah, diamino silver. Right, in the presence of hydroxide. And so I've done this before, and it's pretty cool. It's a little sensitive, but basically what happens is the anomeric carbon, as you can see here in the photo, it gets oxidized from an alcohol group to an ester group, right? So this is actually forms a lactone. In the process, the silver that's present in your silver compound, it gets reduced. Anytime there's a redox reaction, something gets oxidized, something gets reduced. The carbon, your anomeric carbon gets oxidized, your silver is in the +1 form originally, and it gets reduced, it gets more negative to Ag no charge. That is elemental silver, silver solid. And that is what actually forms as a byproduct on whatever type of glassware that you have. So they showed a Florence flask here. And you see it's basically called the silver mirror because it has sort of a mirror effect. Fun fact. Back in the olden days, and don't ask me how long ago because I don't know, but I know long ago, this is was actually the common way to make mirrors. You would take a pane of glass and you would coat it in a glucose solution. And then you would apply this, by the way, this silver reagent is called Tollens reagent. You would apply Tollens reagent, and so what it would do, it would oxidize the glucose, but in the process it would form elemental silver as a byproduct, and it would deposit, and you would have a mirror. That's one of the reasons antique mirrors that were made in this fashion are so expensive, is because literally they are coated with silver. All right? So, reducing sugars themselves are oxidized. You can have, the other case though, you can have sugars that are themselves reduced. Right? And so, a good example is something called sugar alcohols. So here's an example of sugar alcohols. So you can see, sorry, my voice is really starting to die. If we look at D-sorbose, that's a simple monosaccharide. You see it's got a ketone group in there, right? Ketone group, that carbonyl carbon has 2 bonds to oxygen. If you reduce it from having 2 bonds to oxygen to 1 bond to oxygen, it's going to be in its reduced form, and you form something called D-sorbitol. This is a sugar alcohol. You see another example there with xylulose and xylitol. Right? If you think any of these sound familiar, they should, because this is actually a pretty common sweetener, artificial sweetener that's used in a number of things. You see it a lot in gum. If you ever get like a quote-unquote sugarless gum, they don't have sugars in them, they have sugar alcohols. They're used for diet drinks, low calorie applications because they do have lower calories values than sugars do, right? A sugar alcohol is going to contain about anywhere from 0 to 2 calories per gram, whereas a monosaccharide like glucose is going to have about 4 calories per gram. So it does provide, a little bit less of a caloric intake. And also, it cannot be metabolized effectively by the bacteria in your mouth. So it's better for your teeth than a typical sugar-based gum because the bacteria just can't handle it. And so they don't make the acid byproducts in your mouth. So kind of cool. Very, very dangerous for pets, though, so don't ever let your pets have anything with sugar alcohols in it. All right? Okay, so that's a couple of reactions. There are other reactions, a couple of important ones. We saw this a little bit with, excuse me, with lipids in a previous chapter, right? We saw that there were certain types of lipids that contained sugars that were bonded to either part of the lipid backbone or they had phosphate groups on them, right? So you can absolutely take any of these OH groups and esterify them by reacting them with a carboxylic acid or phosphoric acid to form phosphoric acid esters, right? And that happens quite frequently. The one I'm really going to concentrate on here, though, is something called the glycosidic bond. All right, and this is going to be what's the best way to say this? The main bond? That just sounds too informal. It's going to be probably the most it's going to be the bond that predominates in forming higher level sugars, right? We're going to see, just like with amino acids and proteins, we can start linking these things together and forming other types of sugars, more advanced, complex types of sugars. Right? Here's an example. Basically what happens when you form a glycosidic bond is that you take the OH group on your anomeric carbon and you react it with another hydroxy group. And you end up with a linkage. It looks really, really similar to an ether linkage, right? So if I take what was on that slide and I kind of draw it out, they did a reaction between something called alpha-D-glucopyranose and methyl alcohol, or methanol. Okay, so this is your glycosidic bond right here. At the anomeric carbon, you used to have an OH, right? The H basically got replaced with the CH3 that came from methanol, right? So you basically lost an OH from the methanol. You basically lost an H from your anomeric OH. So you give off H2O as a byproduct. This looks really, really similar to an ether linkage. If you remember from organic chemistry, this is what an ether linkage looked like. An O, basically between two R groups. And that's kind of what you have here, but we don't call it an ether linkage. This is actually an acetal linkage. So you remember when we talked about hemiacetals, right? Let me go backwards a little bit. We said a hemiacetal looked like this. Ah, that's ugly. That's supposed to be an R group. Okay. An acetal looks very similar. Except now we have two OR groups instead of just one. And that's what we have here. Here's one of our OR groups right there. Here's our other OR group. Here's our R group. And we didn't draw it, but the H is still there, right? So, when we form a glycosidic linkage, we basically convert our hemiacetal into an acetal, or a full acetal. Same thing with if we had a hemiketal, right? We had a hemiketal form and we formed a glycosidic linkage to it, we would convert that into a ketal. Sorry, I took a break there to swig some Coke. Hopefully it'll make my voice go a little bit better. Okay. Okay, so that's how you form a glycosidic bond. And so sometimes you can form a glycosidic bond with just, other alcohols. But the most important ones are going to be where you actually form bonds, glycosidic linkages between OH groups on multiple sugar units, right? This is how we start making higher level saccharides, right? So if we get put two of them together, that's a disaccharide. If we put three of them together, that's a trisaccharide. If we put a bunch of them together, then we start getting a polysaccharide. All right? So let's start off with just making, a disaccharide. The first thing to remember is that, we said that anomeric carbon I'm going to be lazy here and just draw the important part for this point. We said that this OH group that's on the anomeric carbon, it could be pointed up or it could be pointed down. Okay? Depending on whether it's pointed up or down, that means we're going to make either an alpha linkage or we're going to make a beta linkage. Excuse me. Hold on, I'm trying to find my spot in the book. Give me a second. All right. Oh, my kid's trying to... All right. My kid's trying to call me. Might be important. I'll make a part 3, so we'll pick it up there. All right. Bye-bye.